Hi guys, today we're going to be going over Chapter 3, Section 2, Ocean Chemistry and Structure. What we want to focus on today are the physical properties and then the chemical properties of seawater, because of course that shapes the life in the oceans. Fundamental properties such as light level, pressure, transmission of light, and sound are drastically different in the oceans than they are on land. So let's look at transparency first. Water is relatively transparent, meaning that you can see through it. This means that sunlight shining on the surface can penetrate the surface to some level, which is crucial for the photosynthetic organisms that live in the upper level of the ocean. They need sunlight to do photosynthesis. A Secchi disc is used to measure water clarity. This simple device is lowered into the water until it cannot be seen anymore, and that gives you a measure of transparency. The level of penetration also greatly varies depending on the materials dissolved in the water. The more materials or the type of materials could make the water more cloudy. Different colors of light penetrate to different depths in the ocean. Blue light penetrates the deepest of all the colors, while the others get absorbed. Here you can see in this graphic, red is quickly absorbed, then orange, yellow and purple about the same, green, and then finally blue. Blue is visible down to about 65 meters. So as you go deeper, objects lose their true color and they look blue, because blue is the only light that's getting down that far. And then by the time you get to 1,000 meters, only darkness remains. But here you can see this starfish at 30 meters, where only blue light remains. The sea star, which naturally would look white with red tips, at 30 meters below looks blue with almost black tips. And that's because as you go deeper, objects lose their true color and look blue, which penetrates the deepest. Now let's look at pressure. You think about when you jump in a pool and you go down to the bottom, you can already begin to feel the pressure of all the water pushing on you. So we know that pressure increases dramatically with ocean depth. Organisms on land are under 1 atmosphere of pressure at sea level, 1 atm. But marine organisms are under the weight of the atmosphere and the weight of the water. So let's look at how much that increases. Well, with each 10 meters of depth, every time you go down 10 meters, another atmosphere of pressure is added. Again, atmospheric pressure is the pressure of the atmosphere on you. It's called 1 atm, and that's what it is if you're standing there at the beach. But once you go down underwater 10 meters, it's like you have 2 atmospheres on top of you. If you go down to 20 meters, it's like you have 3 atmospheres on top of you, and so on and so forth. Now, as this pressure is increasing on an organism under the water, the gases in that organism are also compressed. And changing pressure can affect marine organisms, and of course it affects the scientists that study them. So you have to have some knowledge of how pressure works to be able to work in this underwater environment. Here you have a graphic that kind of shows you adding up the atmospheric pressures at 10 meters each depth. If you look at the balloon, here's what it looks like under 1 atm. And you go down, you double that to 2 atm. You go down to 5 atm. It continues to get compressed until, if you're at 10 atm, it would look much smaller. Now, this video, you could look it up. Herbert Nitsch, he has the record for the deepest diving man. He does what we call free diving, meaning that he holds his breath and dives very deeply. He can hold his breath up to 9 minutes. He's trained himself to be able to do that. So it's pretty interesting video. This girl also is able to free dive quite extensively, and she talks about how the pressure affects the gases in your body and your lungs as you dive. All right, let's talk about sound for a minute. You know, water is denser than air. So how does that affect sound? Does that mean sound can travel faster in water or slower in water? Well, the higher density of water actually causes sound to travel 4.5 times faster in water than in air. If you want to look at the meters per second, it's 340 meters per second in air, but about 1,520 meters per second in the shallow ocean. There's actually a section of the ocean called the Deep Sound Channel, also known as SOFAR. It's a channel where sound waves can travel uninterrupted for thousands of kilometers. And we know that this naturally occurring channel is used by whales and other creatures to talk to each other over hundreds and even thousands of miles. So I put a picture of it in here. SOFAR stands for Sound Fixing and Ranging Channel. It's a naturally occurring ocean channel that allows sound to carry great distances. Usually it's low frequency sounds. So that we know that because we detected it back maybe 100 years ago using hydrophones and being able to receive sounds that were miles and miles away. They did an experiment where they blew up something and they were able to record it, even though it was, I think, maybe 300 miles away. They were able to receive the sound of that explosion in the hydrophone. So whales particularly use the SOFAR to communicate with each other, to sing to each other hundreds and maybe thousands of miles away. Not just whales, though. Fish, marine mammals, and shrimps, other marine mammals and shrimp, use sound for communication, navigation, reproduction, and predator and prey detection. Now, the chemical properties of water. We'll go ahead and include this in this 3.2 video. The chemical properties of seawater distinguish it from freshwater habitats. The term that we use is salinity, and that refers to how much salt is dissolved in the water. The salt composition. Now, we talked about this the other week, but salinity is the total amount of salt dissolved in water. And there's a couple other things dissolved in the water as well, but salt is the major component, and it's usually expressed as the number of grams of salt dissolved into 1,000 grams of seawater. So, for example, if 35 grams of salt were dissolved in 1,000 grams of seawater, then the seawater has a salinity of 35 parts per thousand, or it's expressed as you see here with this symbol. There are 6 other ions that compose more than 99% of the material dissolved in seawater, and you see them listed here. But sodium and chloride account for 85% of the ions, which is what make up table salt, and that's why seawater tastes like table salt. Where do these ions come from? We talked about this earlier, but they come from volcanoes and hydrothermal vents. Those are, of course, sulfides and chlorides. And then the rivers that empty into the ocean tend to bring sodium, potassium, and magnesium ions. Now, what's really interesting about the ocean is that, for the most part, the oceans are chemically well mixed. If you sample seawater from various oceans, you're going to have pretty similar amounts of salinity. If there are variations, it's usually the result of the addition or removal of pure water. So, for example, think about the surface of the ocean where the sun shines. Water is constantly evaporating from the surface of the ocean. So the water that you find along the top, the salt doesn't evaporate. So the water that you find on the surface tends to be a little more salty because of the water being evaporated. Also, if you think about hydrothermal vents, those proportions of salinity are a little different right there because, of course, you're adding lots of minerals at that location. Where rivers flow into the ocean, that also changes the variations of salinity. And then if there's a lot of biological activity, so for example, if there's a lot of photosynthetic organisms or an algae bloom, a lot of microorganisms can affect the salinity temporarily in an area. But usually the average salinity is about 35. The saltier the water, the denser it is. That's why it's easier to float on salty water. Here's a picture. People like to go to the Dead Sea, which has super high salinity, and take pictures floating, reading a book, just chilling, because it's very easy to float there. Now, what is making the water denser? Well, in this case, it's the saltiness. There's more salt in that water, which makes it more dense. But temperature also can affect density. And temperature does considerably vary in different oceans. Obviously, we've got our Southern Ocean and Arctic Ocean, which are much more cooler than oceans that run along the equator. So temperature varies considerably. And it actually affects density more than salinity does. So the warmer the water, the less dense it is. The cooler the water, the more dense it is. So cooler water sinks, and that's why usually at the bottom you have cooler, saltier water. Now, there are some other trace elements, nutrients and organics, that get into the ocean. Those are usually metals and metalloids, and they enter the ocean through river runoff, groundwater seeps, the atmosphere, but they're in very small amounts. And then what happens to them is they kind of collect together with other particles, and they actually sink to the bottom. So they end up being down in the sediment at the bottom of the ocean instead of floating around in the water. And so as they fall, the particles that they are stuck to, as they fall through the water, they're called marine snow. And these elements are also nutrients for the creatures that live towards the bottom. So it's a good thing that they're falling, because they're used up by creatures that catch them that live down in the deep. So the question, does it snow in the ocean? Yeah, it sure does. It's called marine snow. And so as it trickles down, this picture just kind of demonstrates how organisms will eat marine snow, and then when they poop it out, it continues to fall, and other things eat it, and it continues to fall, and other things eat it. So something could be eaten, a particle could be eaten 7 or 8 times on the way down. And that's part of the trickle effect of marine snow that makes life possible on the bottom of the ocean. All right, that's all we have for today. Oh, no, one more thing. Dissolved gases. So many gases are also dissolved in seawater, including oxygen, carbon dioxide, and nitrogen. So where does oxygen come from? Well, oxygen is produced by creatures that do photosynthesis, marine plants, and the phytoplankton. And we'll study both of those in a later chapter, but they are both doing photosynthesis, so they're releasing oxygen into the water. There are gases that come from the atmosphere and dissolve right into the water. Now that's pretty important. Let me repeat that. Gases in the atmosphere actually will dissolve into seawater at the surface. And this happens all day long. It's called gas exchange. Now, carbon dioxide is, on the other hand, well, it's one of those ones that comes into the seawater from the surface. It's involved in that gas exchange. And that carbon is very important because it forms the backbone of all the organic molecules that are going to be used in the ocean. So the carbon that forms the backbone of all organic molecules starts in the atmosphere as carbon dioxide, and then it dissolves into the ocean through this gas exchange. Once it enters the ocean, it's converted into organic compounds by photosynthesis, by those plants and those phytoplankton. They use carbon dioxide, just like land plants, to do photosynthesis, and that releases oxygen. On the other hand, consumers, decomposers, and producers, the animals, are breaking down oxygen and releasing carbon dioxide, just like we do on land, which is then available for the producers again. So just like we have the cycle on land where plants make oxygen and animals breathe oxygen and release carbon dioxide, and plants take in carbon dioxide to make oxygen, we have that same cycle happening in our oceans. So this picture just kind of demonstrates all what's happening over in the ocean, which I just mentioned, just like it does on land, but it also shows you some different movement of carbon all over the planet, where you start out with carbon in the atmosphere, There's a lot of ways carbon gets in the atmosphere. As you can see, you've got animals that breathe out carbon dioxide. When things decompose after death, that releases carbon dioxide. When things are burned, plants and forests are burned, that releases carbon dioxide. And of course, any kind of burning. So factories that burn things, that combustion is releasing carbon dioxide. And usually that's referring to fossil fuels. So when you're burning gasoline in your lawnmower, in your car, that is all putting carbon dioxide into the atmosphere. Now, you'll notice the arrow on the right shows the carbon dioxide entering the atmosphere from the ocean. It's also diffusing into the ocean. And I have an arrow there that says gas exchange. So carbon dioxide is actually diffusing into the ocean all the time at the surface. And if there can be a problem when there's too much carbon dioxide in the ocean water, and we'll talk about that next time.